All right, so we worked on formulas for rectangles, parallelograms, triangles, trapezoids, all those straight line polygons, using multiplication, largely some algebra. So for a circle, it's a little bit more of a mystery. The formula for area of a circle is pi times r squared, and you've seen that formula before, so it shouldn't be new to you. But we're going to work with it and try to develop some things about it throughout this lesson. So in exercise 1, what we're doing now, so we're looking at an equation of a circle, and we mentioned equations of a circle before and said that when it's centered at the origin, it's x squared plus y squared equals radius squared. When it's not centered at the origin, what ends up happening is the x coordinate could get shifted horizontally. So we have that component, and we also can shift the y coordinate vertically, and that still equals radius squared. So what the h and the k are showing, this h is a horizontal shift, and the k is a vertical shift. Okay, so when I see a 2 after the minus sign, that tells me that this was shifted 2 units to the right, and so the center point, let me actually write that. Center point is at 2, instead of 0, it's at 2. It's moving 2 units to the right because that's a positive 2 that was plugged in after the minus sign. The only way this turned into a plus is if I plugged in a negative 5 after the minus sign. And so that's what turns it into a positive 5, so it's 5 units down. So if I was doing a graph of this circle, 2 units, 5 units, this is where it would be located as a center. Now the radius squared is 36. We talked about this before as well. The radius squared is 36, which means that the radius itself would be 6 if I do a square root. So if I was graphing this thing, I would count 6 units in each direction and make my circle surrounding that point. But anyway, in terms of this problem, we want to know the area of this circle. So radius is 6, which is really all we need to do. And so its area equals pi times radius squared, which would be 6 squared. We don't square the whole thing, we only square the radius. So this area is 36 pi. And the closest on here to 36 pi is 113. So that's choice 4. So a little background on how the equation works, and then using the radius we can get the area. Okay, so circular objects are often added on to other shapes. We've seen these composite figures before. This one's about radius and not perimeter, area and not perimeter. So the area of the rectangle is very clearly 80. I'm not going to get too much into that. But the area of the semicircle, what we have to do is take the formula for area of a circle and multiply it by a half. So I need the radius. Diameter is going to be 8, so the radius must be 4. That's just taking the rectangle, translating it over, and cutting it in half. So I have 1/2 pi times 4 squared. 4 squared is 16, half of that is 8, so that's 8 pi. It wants me to, well, it looks like all of these are still in terms of pi. So because this is multiple choice, I'm going to add the 80 plus the 8 pi, that's choice 3. And that's my final answer. Now, if this was not multiple choice, you would want to read the directions carefully to see if an exact answer is asked for or if an approximate answer is reasonable. Approximate answers, you just put that in your calculator, you type it up, you get a result. Exact answer would need to be left in terms of pi. So since that has a pi and the 80 does not, you don't combine them, you just leave it alone at that step. Okay, exercise 3, we have an inscribed triangle, which means that all of the angles, vertices are on the edge of the circle. AMC is a diameter, that's nice, that tells me there's going to be semicircles, there's going to be a right angle at B. All right, and the radius of circle M is 13, I should draw that everywhere I see it. Okay, and the length of BC is 24, so we can put that in too. All right, so determine the shaded area to the nearest whole number. Now, sometimes a shaded area can be calculated directly. Sometimes you have to calculate it indirectly, and this is one of those times. I've got all these different pieces of the circle. I can get this part directly. I can just do area of a semicircle and be fine. But these other parts are not semicircles, and they're not sectors coming from the center, so I really can't calculate them directly. What I'd like to do instead is do the area of the circle and subtract out the area of the triangle. And if I can do that, then I'll have the area of the shaded. Okay, so the area of the circle is going to be pi times radius squared, so pi times 13 squared. All right, that comes out to 169 pi. And the area of the triangle is going to be 1/2 base times height. Now the base I know is 24, the height I would have to calculate here. And that's just a quick Pythag. It's 24, put an x over there, 24 squared plus x squared equals 26 squared. That's actually a Pythagorean triple. So what that means, I can reduce the 26 to 13 by 2, 24 reduces by 2. The missing side would be 10 because it's 5. 13, 12, and 5 make a Pythag triple, but solving Pythagorean theorem would give me 10 as well. So x equals 10, which means that now I know the base 24 and the height 10, and I can get that area, which would be 120. Okay, so if I subtract circle minus triangle, then I have my total. So the area of the shaded is 169 pi minus 120. It wants to the nearest whole number, so I would put that in the calculator. Comes out to approximately 411. All right, so shaded area problems, if you can't calculate it directly, look for an indirect way to do it. All right, exercise 4. So we have, looks like an ice cream cone laying on its side, but it's a semicircle attached to an isosceles triangle. All right, so determine the area of the semicircle to the nearest tenth of a square inch. Well, in order to determine the area of the semicircle, I've got to know the radius. So I need to know that segment right there. All right, so how am I going to do that? So it looks like what I need to do is calculate this using the triangle. What if I split this in half? And that makes 20 and 20. Well, now I think just some basic trig, right? This is my opposite side, this is my hypotenuse. If I just do sine of 20, I'm going to have r over 10. So r is 10 sine 20, right? So if I do the area of a semicircle, it's 1/2 pi r squared. I can put that 10 sine 20 right in here. 1/2 pi times 10 sine 20 squared. And as long as you're careful with your parentheses, your calculator can handle this entire line and save the rounding for the very last step. Should get 18.4. If you round intermittently, you might have gotten something different. So like if you use 3.14 there, or if you got a decimal answer for radius, that's going to change the rounding, so it might not have been exactly 18.4 for you. All right, so exercise 5. Consider a circle whose radius is a 1/2 inch. Do the circumference and half circumference. All right, so circumference we remember is 2 times pi times radius. So in this case, 2 times pi times 0.5. 2 times 0.5 is 1, so it's just equal to pi. And it wants it to 3 decimal places, which is 3.142. Okay, so c over 2 is equal to pi over 2, because the c was pi, so c over 2 must be pi over 2, which is about 1.571. All right, so now examine the additional handout on the circle dissection diagrams. That's on the next page. So on the sheet, the same circle has been sliced repeatedly and rearranged. First one is shown here. So what must be true of the area of the rearranged compared to the area of the original? They have to be the same. If I take the same 4 quarter circles and I just rearrange them, I haven't changed the area, I've just changed the arrangement. All right, so as the number of slices or sectors increases, what does that shape start to resemble? Now hopefully as you look down that page on 21, you are seeing as the number of sectors increases in the circle, it should be looking to you more and more like a parallelogram. Because what happens is these rounded edges on the circle sectors, they become smaller and smaller to the point where when you line them up, it's almost imperceptible that they have a curve. If you look at that n equals 30 circle, you can barely tell that those sector arcs are even curved. So it's becoming more and more like a parallelogram all the time. All right, so the rearrangement is starting to form a p-gram or parallelogram. Okay, so part C, what value does the height of the rearrangement continue to get closer to? Well, the rearranged version, if I look at this here, the height is, can't call it a height really because it doesn't even look like a parallelogram yet. But using this and thinking about the n equals 30, the height tends to be closer and closer to that radius. All right, so as we get bigger and bigger in the number of sides and more like a parallelogram, the height tends to be trending toward the radius, and the radius of this figure was 0.5. What does the base get closer to? Well, let's look at that too. The base of this non-parallelogram here would be 2 arc lengths, right? And every arc length is equal to, well, every sum of the arc lengths, both bottom and top, is equal to half of the circle circumference. So if you look at your n equals 16, there's 8 arcs. If you look at your n equals 30, there's 15 arcs. It's always half of the circumference. So the base is going to be equal to, or approaching, half of the circumference, which was pi over 2, looking above in number 5. So what is the value of the, what is the value of the area approach? Well, the area of the parallelogram is base times height, if it was in fact a parallelogram. So in this conjecture here, we're saying that the base is pi over 2, and the radius was 0.5. If you multiply pi over 2 times 0.5, what does that area come out to? Well, it's approximately pi over 4. So think of this 0.5 as a half. Pi over 2 times 1 over 2 would be pi over 4. All right, now exercise E. If the radius is r instead of 0.5, fill in the diagram below. All right, well, the height of the parallelogram was continuously r, and the width was continuously pi times r. All right, so the area of this thing must be pi times r squared. All right, length times width would be pi times r squared. So that's just another way to look at area. If you take a circle and you separate it into multiple sectors, they start to resemble a parallelogram whose height is the radius, whose width is half the circumference. So it does come out to be close to pi r squared.